In the realm of machine learning and data science, defining parameters for a job is a crucial step in preparing a model for deployment. Parameters are the variables that influence the behavior and performance of a model. They can be categorized into hyperparameters, which are set before the learning process begins, and parameters, which are learned from the data. Understanding and correctly setting these parameters can significantly impact the efficiency and accuracy of your model. Job parameters play a pivotal role in the deployment of machine learning models. They determine how the model will process data, make predictions, and adapt to new information. Properly defined parameters ensure that the model performs optimally in real-world scenarios. They help in fine-tuning the model to achieve the best possible performance, balancing between underfitting and overfitting, and ensuring that the model generalizes well to unseen data. Hyperparameters are external configurations set before training a model, such as learning rate, batch size, and number of epochs. They are not learned from the data, but are crucial for guiding the learning process. Parameters, on the other hand, are internal to the model and are learned during training. These include weights and biases in neural networks. Both types of parameters need careful tuning to ensure the model's success. Setting hyperparameters involves a combination of domain knowledge, experimentation, and sometimes automated techniques like grid search or random search. For instance, the learning rate controls how quickly a model updates its parameters. A too high learning rate might cause the model to converge too quickly to a suboptimal solution, while a too low rate might make the training process excessively slow. Similarly, batch size affects the stability and speed of the training process. Parameter initialization is a critical step in training neural networks. Poor initialization can lead to slow convergence or even prevent the model from learning. Common initialization techniques include random initialization, Xavier initialization, and He initialization. These methods aim to set the initial weights in a way that avoids issues like vanishing or exploding gradients, ensuring a smoother training process. Regularization techniques are used to prevent overfitting, ensuring that the model performs well on unseen data. Common methods include L1 and L2 regularization, dropout, and early stopping. L1 regularization adds a penalty equal to the absolute value of the magnitude of coefficients, while L2 regularization adds a penalty equal to the square of the magnitude. Dropout randomly sets a fraction of input units to 0 at each update during training, helping to prevent over-reliance on specific neurons. Cross-validation is a technique used to assess the performance of a model and ensure its robustness. It involves partitioning the data into subsets, training the model on some subsets while validating it on others. This process is repeated multiple times, and the results are averaged to provide a more accurate estimate of the model's performance. Common methods include k-fold cross-validation and leave-one-out cross-validation. Automated hyperparameter tuning techniques, such as grid search, random search, and Bayesian optimization, can help in finding the optimal set of hyperparameters. Grid search involves an exhaustive search over a specified parameter grid, while random search samples a fixed number of hyperparameter combinations from a specified distribution. Bayesian optimization builds a probabilistic model of the objective function and uses it to select the most promising hyperparameters to evaluate. Monitoring and logging are essential for tracking the performance of a model during training and deployment. Tools like TensorBoard, MLflow, and custom logging scripts can help visualize metrics such as loss, accuracy, and other performance indicators. Effective monitoring allows for early detection of issues, enabling timely interventions to adjust parameters or modify the training process as needed. Parameter sensitivity analysis involves studying how changes in parameters affect the performance of a model. This analysis helps in understanding the robustness of the model and identifying critical parameters that have a significant impact on performance. Techniques such as one-at-a-time (OAT), sensitivity analysis, and variance-based methods can be used to systematically evaluate the influence of each parameter. Consider a case study where a neural network is trained to classify images. Initially, the model might perform poorly due to suboptimal hyperparameters. By systematically tuning the learning rate, batch size, and number of epochs using grid search, the model's performance can be significantly improved. This case study highlights the importance of hyperparameter tuning in achieving optimal model performance. Best practices for defining parameters include starting with a simple model and gradually increasing complexity, using cross-validation to evaluate performance, and employing automated hyperparameter tuning techniques. Additionally, keeping detailed logs of experiments and results can help in tracking progress and making informed decisions. Collaboration with domain experts can also provide valuable insights into setting appropriate parameters. Defining parameters for a job is a critical aspect of preparing a model for deployment. It involves a combination of domain knowledge, experimentation, and automated techniques to ensure optimal performance. By understanding the importance of parameters, setting them correctly, and employing best practices, data scientists can significantly enhance the effectiveness of their models. The next steps involve applying these principles to real-world projects and continuously refining the process based on feedback and new developments in the field.